Okay, maybe we should get started. Okay, all right. So last time I introduced the concept of the Lie algebra of a group, of a Lie group. So remember, a matrix Lie group is a closed subgroup of GLNC with the induced topology from and by matrices on GLNC, and we defined the Lie algebra of such a Lie group to be the set of elements of GLNC with the property that the one parameter subgroup that passes through this element or is generated by this element is contained in G. So the picture would be that so you can imagine that this is G, and for different vectors at 0, there are different one parameter subgroups, and some of them might be contained partially or maybe not at all in G, and some of them are fully in G. So the set of vectors X which generate the one parameter subgroup in G is denoted to is called the Lie algebra, and we are going to show that in fact it is a Lie algebra. Okay, so this is the goal today, to study this Lie algebra. First, to prove that this fracture G is a Lie algebra, and then study properties of this. So one of the key tools for today is something that we studied a couple of lectures ago, and that was the Lie product formula and the commutator formula, which is the following. If you want to compute the exponential of the sum of two matrices, in general, it's kind of hard to relate it to e to the x and e to the y. We will see some relation more complicated than that, which is called like the Baker-Campbell-Hausdorff formula. But here is a sort of a limit form of this, like a limit statement connecting e to the x plus y to e to the not e to the x and e to the y only, but the elements of the one parameter subgroups generated by x and y. So this is going to be a key statement in today. So just to remind you of this statement, any questions about this statement? You remember this statement, hopefully, this theorem. Okay. The Lie product formula, which we proved a couple times ago. Okay, everybody happy with that? All right, so now back to the goal today. So the first thing is to show that what we have, this G, is indeed a Lie algebra. Okay. Now, remember, last time I also mentioned that this G only depends on the connected component of identity, because e to the tx belonging to G is equivalent to e to the x belonging to G naught, the connected component of identity, because this is a path from identity to e to the tx. All right, okay. All right, so here is the theorem, the key theorem. So let G be a matrix Lie group. And let G be the set of, maybe I should write G inside GL and C. It's the set of elements in M and C, such that for all T in R, e to the tx is in G. Okay, so now let x and y be in G. Then the following properties hold. The first is that conjugation by elements of G, by elements of capital G, will produce elements of little g still. So this is true for all A in capital G. Conjugation by capital G leaves, unlike the curly G, the fracture G, stable. The second is that G is stable under dilation, which means like Sx is in G for all scalars in R. The third is that, in fact, G is closed under addition. So 2 and 3 imply that we have a subspace. And the fourth, sorry, is that the usual matrix commutator of x and y will also belong to G. So this guarantees that G is a Lie subalgebra of GL and C. So it's closed under the bracket of GL and C, which is xy minus yx, matrix xy minus yx bracket. All right, so let's prove these assertions. Okay. So for the first statement, so we have to show, well, what should we check? We should check that e to the ax a inverse, like e to the t times ax a inverse, belongs to g, little g, for all parameters t. But we know, well, we can write this as e to the a times tx a inverse. And we know that if you conjugate the argument of matrix exponential, you could bring the conjugation outside because of the power series formula, right? So you could write this as, like we've seen this before. This is e to the tx, a e to the tx a inverse. So now what you have is a some element of g, and it's conjugated by a. Conjugation by g of elements of g will still produces elements of g. And this is true for all t. Hence, sorry, I think I wrote an a t inverse. I should have written an a inverse here. So ax a to the minus 1 will belong to g. Okay, so stability under conjugation is like verified. Any questions? Okay. And number 2 is also easy. It's like dilation invariance is also easy. It's just like by definition. So you want to show that like e to the sx, well, you want to show that sx is in curly g. So you want to show that this e to the tsx belongs to capital G for all t, but this you can write as e to the ts times x. And this is a new scalar. In R, we know e to the any scalar times x is in G by definition of x. By definition of G, since x is in G, okay? So this means now that Sx is in G by definition of like the algebra, so to speak, okay? The third one, however, becomes a little bit trickier. So we want to show that e to the t x plus y belongs to this curly G for all t. Okay, we know e to the x and e to the y are there, but we cannot write this as e to the tx times e to the ty because x and y do not commute. However, still, we can write this as a limit of e to the t x over m, e to the t y over m. I'm sorry, I forgot the powers to the power m. The power is actually outside, sorry, okay. So e to the t y over m to the power m as m goes to infinity. So it's a product of two m points, m of which are in the one parameter subgroup of the form e to the tx. Maybe I should write it gamma xt. So they are on gamma xt, which is e to the tx. And these guys are on gamma yt. Okay, so we have, so this guy is a limit of points on G. So this product is in G, and we know it converges to this. So it's a convergent sequence, but it's a sequence of points in capital G. So since G is closed, the limit, which we know exists by these theorems. So this is, maybe I should write like a leap product formula. So the limit belongs to G. And now this implies that x plus y is in G. This is for every t. So maybe I should just add here for every t. For every t, we have verified that this quantity is indeed in G. And therefore, x plus y should be in G. Okay? So the argument requires this trick. And you will see that we will use this trick a few times today and later on. Okay, any questions? And now what about part 4? We want to show that G is closed under taking the commutators. Well, you can describe e to the t times the commutator as this product of e to the x over n squares and e to the 1 over n squares. You remember we had this expression like called the commutator theorem. Just the same theorem, Lie product formula had a commutator version. We can use the commutator theorem, or I give a simpler proof because the commutator theorem was a little bit complicated to prove. So use the commutator theorem. Or, well, I want to show that this Lie bracket is in G. So now again, there's another trick. It's simpler, but there's still a trick. So if you look at this quantity, e to the tx, y e to the minus tx. So in other words, I'm looking at this path, gamma of t equals e to the tx, y e to the minus tx. Okay? So now I would like to differentiate this at 0. This is a differentiable path. You know, it's linear, like vector calculus, basically, because the exponential is differentiable, and this is a product of things. Every entry is like a function of the like a power series in t. Like it's like a nice power series in t coming from the exponential. Okay, this is vector calculus. All right, so I just want to differentiate. So since I'm using vector calculus, you should be able to tell me which rule I should use to differentiate them. How can I differentiate this? Yes, I want to differentiate with respect to t. It's like a one parameter differentiation. It's a function from R to some Rn squared. You know, this is like matrix space. So how do you differentiate such a thing?
Oh, it's not a y in the middle. It's a 2 brackets.
In the middle is y. Yes, it's a y. Yes. But in calculus, you know, how would you differentiate some inner product of two vectors if you wanted to do this? How would you do that? This is the Leibniz rule, exactly, the product rule. I mean, the same rule applies. You differentiate the first times the second at the evaluation point, plus evaluation of first times derivative of the second. Same rule applies here and also to matrices, because really matrices here are just vectors. Everything is like, it's vector calculus. Maybe I just add vector calculus calculation. All right, so I should differentiate the e to the tx at 0, but the derivative of the exponential will be like, what is the derivative of e to the like a ta at t equal to 0 for a number? And well, you have to so this is now, you now use the chain rule, and you should be able to use the chain rule.
This 8.
Yeah.
It's 8.
Yeah, that's like a e to the ta, you evaluate at t equal to 0, the e to the ta will go away. So you just get a, right? E to the 0 is 1, right? So when you differentiate the first guy here, you get x, all right? And then you evaluate this guy at 0, the e to the minus tx will disappear. It becomes the identity matrix, so you end up with y. So you get x times y. And now you have to add, now you evaluate the first guy, it will be identity times the derivative of this guy. The y is a constant, you know, so therefore you have to differentiate the e to the minus ty. So what do you get? The e to the minus tx, sorry. What do you get when you differentiate this at 0? The t should disappear. I mean, because you evaluate equal to 0. You get minus 1, because if I differentiate e to the minus ta, I get minus a at equal to 0. Okay? Everybody happy? This is calculus. Are you following me? Okay, this is good? All right, okay. So I get minus x. So I end up with xy minus yx, exactly what I wanted, right? But now, well, why did I prove what I wanted? Well, here, okay. So now, but we also had conjugation invariance. That was part 1. So part 1, we showed that there's conjugation invariance of this curly G under the group G, right? So now e to the tx, y, e to the minus tx is in G. This is by part 1. because this guy, because x comes from curly G, so e to the tx is in capital G. And this is just the inverse of that guy. So this is also in capital G. And this is in G. All right. So we know that this whole thing, this quantity that we are differentiating lies in this subspace G. Okay. So now, again, we need vector calculus. So if we differentiate, so here's a remark. So if gamma from R to V, where V is a vector space, and image of gamma is contained in some W, some subspace, vector subspace of V, then gamma prime at any point is also in the subspace. This is clear, right? Because the tangent space is the same, right? So, I mean, maybe it's easier to see in 3 dimensions what's happening. So in 3 dimensions, suppose I take this hyperplane and I take this path, this curve, which completely lies in this plane. So where are, like, what does the derivative, oops, why does it disappear? Oops. What does the derivative mean at any point? Derivative means the tangent vector. And if a path lies in some hyperplane, the tangent vector should lie in that hyperplane. This is calculus again, okay? Do you agree this is calculus? Okay, all right. All right, so this means, so now, just to like maybe write more precise argument, so now, so if gamma t equals e to the tx y e to the minus tx, then image of gamma is contained in G, and G is a subspace. This is important, hence the derivative of gamma at 0 also belongs to this subspace. But what we know is that this derivative, we just computed this derivative, that's just xy minus yx, as we just calculated above, right?
Can you prove that the statement you just said about the derivative being a subspace?
Can I prove this?
No, I'm asking with the definition and saying that every subspace of a finite dimensional space is closed.
What do you want me to prove?
I'm asking if it's possible.
To prove what?
That
this remark?
The derivatives. Yeah.
Using what?
That it's just the definition of derivative, and then that.
Yeah, I mean, if like, okay, so let's assume V is finite dimensional. I mean, we are not differentiating in Banach spaces yet, okay? So if V is finite dimensional, all you need to do is choose a basis for W and write gamma in those coordinates. When you do that, then your function gamma will be like a, you know, in the basis coordinates of W, it has something, but then it has 0, 0, 0. When you differentiate zeros, you just get zeros. Okay. Okay, is it clear? Everybody happy with this? Okay, so now, maybe we should scroll up a little bit and look at this for a moment. So here I showed that for any real scalar, if I scale an element of G, I end up in G in the Lie algebra. But what about complex scalars? Is that also true? We're not assuming that, and it doesn't have to be true, because we have, say, SL2R, which is like a Lie group, and its Lie algebra is SL2R, the Lie algebra, matrix of trace 0 with real entries. They're not closed under complex scalars, right? And the argument really used the fact that the scalar is real, because the definition of the Lie algebra is using a real scalar, not a complex scalar. Okay, we don't want to do the complex scalar, but if it turns out that even G is closed under complex scalar multiplication, then we call this G a complex Lie algebra, and the corresponding Lie group will be a complex Lie group. So maybe I just give this definition. So here's the definition: a matrix Lie group G is called a complex Lie group if G is a C vector space. i.e. ix is in G for all x in G.
You should call it C group.
C group? Why should we call it a C group? Yeah, but then that leads to, well, then the group should be called R groups. In some sense, okay, if we think about algebraic groups, we kind of do, because then we have this notation. We have this GR and we have this GC. You can plug it in any field. So there's sort of like F rational points for any field, R rational points, or like C rational points. This notation is there in a slightly different context, but yeah. Okay. The terminology accepted one is the complex Lie group. Okay. Because we also have complex manifolds. You know, this is also another established terminology. All right, people online, any questions? Jordan? Mohan, you're doing good? Okay, you're following? Everything is okay? Sound is good? All right. Okay, so now here is a simple proposition. Let's try to figure out the structure of this Lie algebra coming from the structure of the group G. So here's the simple one. So if G is a commutative, is like a abelian, maybe I should say abelian, okay? Yeah. I think maybe it's enough. If G naught is abelian, okay, okay, G is a Lie group throughout this course anyway, unless otherwise it's stated. But anyway, so let G be a Lie group, be a matrix Lie group. If G naught is abelian, rather commutative, then G is commutative or abelian. We can call it abelian in the algebra, that's fine. Slash abelian. There's no. So why is this true? So we want to show that if we take x and y in G, we want to show that xy minus yx is 0. Okay, so let's see what it is. So xy minus yx, we just had a formula for it above, right? It was the derivative of something. It was the derivative of this conjugation thing, right? So let's write it out. It's the limit as t goes to 0 of 1 over t. I'm just writing the meaning of the derivative. E to the tx y, e to the minus tx minus y, well, I already divided by t, okay? This is the derivative of this curve at 0. At 0, your gamma of 0 is y anyway, okay? So I'm just writing the meaning of the derivative, and I want to show that this limit is 0. So now I have to show that, in fact, well, it's enough to show that this quantity is 0, e to the tx, y, e to the minus tx. It should somehow follow from the fact that the group is abelian. But let's see why. So let's again write the meaning of y. What is y? Y is the derivative of this one parameter subgroup. So now e to the tx, y, e to the minus x, tx, sorry. This is e to the tx times the derivative of the one parameter subgroup, which is e to the sy, at 0. So basically, it's this ratio. This quantity is y, by definition of y, right? And now it's easy to see why this is actually 0, in fact, because this e to the tx will commute with e to the sy, because they're elements of this group, right? So this you can write as e to the, so this is like limit of, so now t is fixed, right? So this is the limit as s goes to 0 of e to the tx, e to the sy, e to the minus tx minus identity divided by s, which is, I can just write, I mean, because G is abelian, capital G is abelian, I can write this as e to the sy times e to the tx, e to the minus tx minus 1 divided by s, which is e to the sy minus 1 divided by s. And as the limit goes s to 0, you get y by definition of y. Okay, so we just showed that this quantity is equal to y all the time for any s, for any t. Okay? So what's the consequence? Back to here, we have 1 over t of y minus y. So xy minus yx is the limit as t goes to 0 of y minus y divided by t, which is obviously 0. Okay, so I showed that this quantity is equal to y. And therefore, I get 0 in the limit. So xy minus yx is 0. All right, all is good? Now let's compute some Lie algebras. Now that we have a definition and we know that we actually do get a Lie algebra structure, let's compute and see what we have. So this is the proposition, which gives some explicit examples. I mean, the examples are familiar, but now we're just connecting these examples to the corresponding Lie groups. So the first part, the Lie algebra of GLNC itself as a Lie group. Is this Lie algebra GLNC? So this is just n by n matrices. Over C with the usual bracket, the xy minus yx. Maybe I should write it as bracket equals. So. Okay, so this is clear. I mean, because the exponential of any matrix in GLNC is in GLNC. By definition, you see that's what it is. You just have to figure out like what elements have the property that e to the tx is always in the Lie group given. Now the second one, what is the Lie algebra of GLN-R, n by n invertible matrices? What could it be?
So probably complex matrices with the trace that's or trace that's complex, something to do with the trace.
Do we need some trace condition really? What do you think? We need what? We need the trace condition yet?
No, we don't.
The only condition will be on the entries. So it will be GLN-R. So why is that so? Maybe I just give the proof. Okay, before writing the other parts. So one is clear. And what about two? So let's see for which x's we have e to the tx is in GLN-R. So what is the meaning of this? Well, how do you figure out what x is? Well, you can differentiate this at 0. I mean, the main idea really is differentiation at 0. Okay, so differentiate as 0, so derivative. Maybe I just write the derivative. Okay, the d dt e to the maybe okay. So it happens that x, as we know, is the derivative of this one parameter subgroup at equal to 0. Okay, but now this is a derivative of something which is real, like of real matrices. It's in the subspace of real matrices. So the derivative will still belong to the subspace of real matrices. So I just write M and R, and then as a consequence, the result is in M and R. Which is the same thing as GLN-R. GLN-R is just M and R with a natural bracket. Okay. And well, converse is also clear. If you have something in GLN-R, then its exponential will be just a real matrix, which is inverted. Okay. The converse is also clear. Oops. Now here's another example. What about we take the Lie algebra of SLNs? Now here we might need a trace condition. So what is this Lie algebra? Well, we call it this Lie algebra SLNC. I guess I've introduced this notation before, right? This is like elements in GLNC with trace 0. Okay, and why is that so? So first, so it basically comes from the relation that the determinant of e to the x is the same as e to the power trace of x. Okay, so if e to the tx is in SLNC for all t, so then determinant of e to the tx is 1, but this means that e to the power in fact, it's enough. Like if you set just equal to 1, all right? So this means that trace, so e to the, maybe I need the, actually I need the parameter, sorry, okay? So then e to the power t times trace x is 1 for all t, okay? Because the trace of tx is t times trace of x, okay? All right? And as a consequence, well, if then the exponent should be 0. The only way this can happen, you can't have a non-zero number here. Okay, just you differentiate, the derivative will be 0, but the derivative is trace x. It's like the derivative of that e to the t times trace x, that's equal to 0 again. Okay, and the converse is also clear. If you have something with trace 0, then the determinant of this guy is just e to the t times trace. But trace is 0 anyway. So the determinant is 1. So all the arrows can be reversed with no problem. And finally, the Lie algebra of SLNR is going to be this Lie algebra SLNR. So the Lie algebra number 4, the Lie algebra. It's the real n by n matrices with trace 0. Okay? Any questions? All is good? Let's now think about these groups of isometries. Here's the next proposition, which describes the Lie algebras of these guys. So the first part, let's think about the group UN, the unitary group. So the Lie algebra of the group UN is UN, which is the set of elements in GLNC with the property that x plus x star equals 0. X star means bar transpose. Okay, and the argument is easy. So what's the argument? So suppose, so if e to the tx is in the unitary group for all t, well, then this means that e to the tx star is e to the tx inverse, which is e to the minus tx, okay? But the left-hand side is just e to the tx star, because the star goes inside, right? Because then t is real, right? So you get it's equal to e to the minus tx. And now again, d over dt at t equal to 0. The left-hand side is x star. The right-hand side is minus x. And the converse is also clear. The converse just reverse the arrows. If like x star equals minus x, then this is equal to this, and this is equal to this, and so on. Now, what if I think about the group SUN? What is the Lie algebra? So I write it like this: the Lie algebra of SUN, which is the unitary matrices, the group of matrices which are unitary and determinant one. Well, of course, it should be SUN. This should be the notation. It can't be anything else. But what is it exactly? It's the set of elements of UN, this Lie algebra UN, such that
Well, that and zero.
exactly. So just like before, any determinant condition on the group turns into a trace condition below. Okay? And similarly, the Lie algebra of ONC is this Lie algebra. I write ONC, or sometimes people would like to write SONC, because like SON and ON are just different in plus minus one. They're like in the connected component of identity. That's the like their connected component of identity is the same. Okay, so maybe I just write ONC. Maybe underneath I like sometimes called SONs, which is the set of matrices in GLNC with the property that X plus X transpose is 0. I mean, the group SON is related to ON by determinant condition. You take determinant one elements. Now, based on our philosophy, and of course it can be precise, but anyway, as you see, the philosophy is that the determinant condition turns into a trace condition on the Lie algebra. But the trace condition is already there. If X plus X transpose is 0, the trace is also 0. Trace of X is 0. Because the trace of the sum of X and X transpose is like a trace of X transpose equals trace of X. This wasn't true here, because here trace of X star will be the trace of X bar. We couldn't remove that S from here and say it's the same Lie algebra. But here, ON and SON are the same Lie algebra. The groups are not, but the Lie algebras are. Okay, the groups are only different up to up to the disconnected part. Is it clear? People online, you're following? Everything is good? Any questions? Okay. Now, as we know, these are, maybe I should finish this. The last part would be the ONR. Okay, so then the Lie algebra of ONR, the n by n orthogonal group, is just this ONR, which is the same thing as SONR, which is the same thing as all the elements of GLNR with trace 0. I'm sorry, with X plus X transpose equal to 0. There is no trace condition. So now remember, these groups of isometries were defined mostly by some general principle. The principle is that we have some element of GLNC, and the group is the set of matrices in GLNC. Yeah, maybe right here. Such that X transpose JX equals J, or alternatively X star. Maybe I just write respectively JX equals J. Okay, so instead of the X transpose JX condition, I could have the X star JX condition. If I had the transpose one, it would correspond to the orthogonal groups. If I had the star one, it would correspond to the unitary groups. Okay. There's only one issue here. Let me just make sure. Maybe that's okay. All right, fine. So then the Lie algebra of G is the set of matrices in GLNC. And now we have to differentiate this condition somehow. Remember, how do we differentiate such a condition? Well, this x is supposed to be some e to the ty. So we have something like e to the ty transpose j e to the ty, and we have to differentiate this condition, okay? But and compute at t equal to 0, okay? So we use the Leibniz rule, and if you do this, you end up with the following condition. You end up with the condition x transpose j plus jx equal to 0. Yeah. Or in the unitary case where you had the star, rather, you would have x star j plus jx equal to 0. Right? And the argument is really, again, some differentiation, okay? What's the argument? So you have this, so what's the meaning of the some y belonging to Lie algebra? Maybe I should write y is in G. Y is in the Lie algebra of G means e to the ty is in capital G, and this means e to the ty transpose. I just do the argument for transpose. For the star, you do yourself. J e to the tx ty, sorry, equals j for all t. And now again, what should we do? Just differentiate at equal to 0, and then use the Leibniz rule just like we've done before, so that for the left-hand side, we end up with y transpose. Remember, e to the ty transpose is just e to the t times y transpose. So I get y transpose j plus j y transpose, and the derivative of the right-hand side is 0 because it's constant. Okay, so we got the condition, and the arrows can be reversed. Yeah, technically for the reverse, for the converse, you have to differentiate this as an arbitrary t, but then some factor comes out and everything reduces to this relation. Okay, any questions? Huh? Yeah.
Does that formula also define a Lie bracket or no? The one that the Lie algebra as well at x to j?
The Lie bracket is always supposed to be the usual bracket.
Okay.
So the question is when this is invariant under the Lie bracket. So you have to
Right.
I mean, and I think the condition is I don't think we need another condition because we do have a group here, don't we? That's the thing that bothered me for a moment, but then I realized that I have a group. So if I have if x and y are in G, so let's do this calculation. If x and y are in G, then y is the product in G, then you write basically like xy transpose j xy is like a y transpose x transpose j xy. Here in the middle, you get j, so you get y transpose j y, which is j. Okay, so we got a group. So it should pass through the Lie algebra. So this subspace should be closed under the usual Lie bracket, the xy minus yx.
Say you wanted to make a Lie algebra without the usual Lie bracket, and you define this to be a Lie bracket. Would it be a Lie bracket?
This is not a Lie bracket. I haven't written a bracket yet. So I mean, the bracket should be bilinear. It needs two arguments that can vary. Here I have only x that can vary. How do I write a Lie bracket here?
Right.
How do I do that? What is
xpg plus jx?
Okay, so you want to define the bracket of x and j for two arbitrary things, x and j.
Yeah.
You want to define it as x transpose j plus jx.
Right. Okay.
That cannot be a Lie bracket. Well, let's call it y rather than j, okay?
Okay.
That cannot be a Lie bracket because Lie bracket should be skew symmetric. This is not. I mean, the bracket. So as I said, so because we are in the world of matrix Lie groups, the Lie algebra is always equipped with the usual matrix bracket, xy minus yx. That's because this theorem proved that xy minus yx is in G. So it's closed under the usual bracket coming from GLNC, the matrix bracket, x times y minus y times x. Okay. And that's the Lie algebra structure that we consider so far. Okay. We can diverge to the world of arbitrary Lie groups, and we kind of do at a later time, but not right now. Okay, any questions? People online, do you have any questions? And finally, maybe one more example, because we have also talked about the Heisenberg Lie algebra and the Heisenberg group. Here's a simple proposition of a different kind. You know, this is not the kind of isometries, but it's sort of slightly different. So the Heisenberg group is the group of matrices with 1, 1, 1 on the diagonal and arbitrary entries above the diagonal, y, z. We can say that x and y and z are in C or in R. Let's just do this in R. So let G be this. Then what is the Lie algebra of G? Can you give a nice matrix description of this Lie algebra?
That we saw in the other example, right? Where you had the upper.
That's right, strictly upper triangle.
I can't tell if you're asking rhetorical questions, by the way.
Pardon?
Are you asking rhetorical questions?
What is a rhetorical
Do
question?
you want people to
There is a
answer?
sarcastic question, but I don't know what a rhetorical question means.
You want
There's a rhetorical answer in politics, but not in
Do you
mathematics.
want us to answer your questions?
Huh?
Want us to answer your questions or no? When you ask
Of course. I want to like answer, and I do not necessarily expect a correct answer. Let me also, I've always said in my classes that an incorrect answer is better than no answer. An incorrect answer is a good answer. Okay? Because it says a lot of things. First, maybe I didn't explain something properly. Second, other students in class do not understand the same thing. So it's the time to explain this. Okay? Third, you guys thought about it. And of course, fourth, everybody makes mistakes. Even prominent mathematicians can make mistakes on the spot. Okay? So it's always good to sort of think and try to come up with an answer, even if the answer is incorrect. Then we try to fix the answer together. And you learn something. You realize why the answer was incorrect. What was your wrong thinking? And you will not do this again. Okay? So please do answer. The questions are not rhetorical or, I don't know, pedagogical, or I don't know, maybe they are pedagogical, but they're not pedantic. Maybe I should have made, that's what I meant. Okay. All right, so please do, and same with people online. It's a little bit harder to interact, but you can always type in the chat or like, as I said, switch on your mic and say something. If you have a question, you want to make a comment, feel free to interrupt me. That's perfectly fine. Same for people here. And we've done this before in other classes. You've taken many courses with me, so yeah. And you've interrupted me many times also. Anyway, so why is this subspace of matrices the Lie algebra of G? Can you explain what's going on? Well, first of all, if you take some one parameter family, one parameter subgroup, it will always have ones on the diagonal. So when you differentiate, the differentiation should be like component wise, right? For example, your gamma of t, how would it look like? Gamma of t would look like something like a 1, 1, 1, zeros here, and then x of t, y of t, z of t. Okay, maybe let me put the ones in the right positions. So when you differentiate, you're differentiating the components, and the ones will turn into zeros, right? So the elements in the Lie algebra should be of this form. Conversely, if you take the exponential e to the tx for a matrix which is a strict upper triangular, you get a unitriangular matrix, one of the above form. So this justifies that you have the Lie algebra. Okay. So oftentimes you have a group, and you have a Lie group, and you want to write this Lie algebra to study or whatever. So it's good to have kind of a recipe for doing this. Now you have these isometries, and you also have this kind of matrix ideas where to put zeros and ones in the matrices, so you can use these things. Ah, there's a comment in the chat. Good. Okay, question is whether the Lie algebra of other matrix Lie groups can be computed similarly. Yes, Mahan. And in fact, the answer to that is just this proposition, because if I choose this matrix to be skew symmetric, the skew symmetric matrix, like say 1, 0, 1, minus 1, 0, then this G will be the symplectic group. And in fact, this will be the Lie algebra of the symplectic group, which is called the symplectic Lie algebra. So in principle, this proposition answers this question. Any group of isometries of a bilinear form, symmetric or antisymmetric, this describes how to compute this Lie algebra. Okay, perfect. Thanks for asking, though. It was certainly helpful to mention this comment because it wasn't maybe clear why, like to what extent this proposition applies. Okay, so now we have studied a little bit homomorphisms between Lie groups, like group homomorphisms, and now we would like to relate them to homomorphisms between their Lie algebras. The connection is the following important theorem. So let G and H be matrix Lie groups. And let capital phi going from G to H be a Lie group homomorphism, which means a group homomorphism which is continuous. Then there exists a unique linear map, the unique R linear map going from the Lie algebra of G to the Lie algebra of H. So here G is the Lie algebra of G, H is the Lie algebra of H, such that it commutes with the exponentiation, which means that for every element of the Lie algebra of G, well, e to the x is in capital G, so I can compute phi of this guy. And it happens to be the exponential of little phi of x. So the picture is the following. So we have this G and we have this H, and this is this phi here. And we have their Lie algebras down here. And this map little phi goes in this direction. It's a Lie algebra homomorphism. And now we have these exponential maps. The exponential of any element in Lie algebra will lie in G, and the exponential of any element in the Lie algebra will lie in G. And the claim of the theorem is that this diagram commutes. Okay, this is a good way of thinking about this whole thing. Yeah.
If you're talking about complex Lie groups and hence complex Lie algebras, does it also turn out?
That is right. So then in that case, I should assume that this map is a holomorphic map. Then I need this, this map cannot be a continuous map. Yeah, I mean, you can have, because you can, for example, you see as a, for example, even GLNC can be thought of as a real Lie group, and then it does have automorphisms which involve conjugation, right? For example, the map x goes to x bar is an automorphism of GLNC, but the derivative will be just an antilinear map, right? It cannot be a complex linear. Okay, yeah. If you assume that the derivative of phi exists in complex linear, then that does the job. That assertion is correct. Okay. So now, furthermore, so at this point, I didn't say that this is a Lie algebra homomorphism. It's part of the data that comes next. So there are more properties. So furthermore, so something died here, and I thought something died there, but not. Okay. So furthermore, this map phi is conjugation invariant. So phi of G x G inverse equals capital phi G, little phi x, capital phi G inverse for G in G and X in G. Little phi of x, y, the bracket of x, y equals bracket of phi x, y, y. The bracket, again, this is the usual, matrix bracket, but for conciseness, let's write it like that, okay? Okay, so this basically, property 2 says that this phi is a Lie algebra homomorphism. Property 3 is that, in fact, phi can be easily obtained from capital phi. So phi x is the derivative of capital phi to the tx. Oops, I screwed up something here. All right, hopefully not, okay. That's equal to 0 for all x in G, sorry. Okay. So for the previous part, I should have also added for x and y in G. And, okay, so that's it. There are only 3 parts, sorry. Okay, so let's now prove this assertion. Prove the existence of and uniqueness of this little phi. Okay, how much time do we have? Where are we right now? Time. Okay, we have time. Okay, so let me see. What am I doing? And so, yeah, okay. So to find this phi, what we do is we use the fact that any one parameter subgroup is given by some exponential. Remember, if I even look at this phi of e to the tx, phi is just continuous. I'm not assuming that phi is differentiable. I mean, by hindsight, we know that any phi will be differentiable, but we don't make this assumption. Okay, so even differentiability of this is a question, right? Because it's just composition of continuous is differentiable. But now thinking about this as a one parameter subgroup, we have the differentiability that we want. So that's what we do. So we set to choose x and g, and now the map gamma from R to the group H, where gamma of t is phi, maybe I write underneath, phi, gamma of t is phi of e to the tx is a one parameter subgroup. Which means it's continuous, and primarily we have to like verify this. But that's a consequence of the fact that gamma, like phi, is a group homomorphism. Okay. All right. Thus, there exists some z. In fact, you can assume that this is in H, such that gamma of t is e to the power tz for all t in R. A priori, well, from this parameterization of like classification of one parameter subgroups, we know that this z is in the matrix in GLNC. But we know that now e to the tz for every t lies in H, the group H. So by the definition of the Lie algebra, this z should be in H. Okay. All right. So now it's clear what of the value of phi of little phi of x should be. It should be z, right? Because that's the natural thing that commutes. So let's see if this thing works, right? So we set little phi of x equal to z. All right. So this gives a choice right? And now we have to prove a bunch of things. First, we have to verify linearity and so on. So let's first verify linearity of phi. So for this, we verify its dilation invariant and addition invariant, okay? Like preserves addition. What about dilation? So suppose that phi x is z and phi of sx is some z prime. I want to show that z prime is just sx, all right? So then what do I know? So I know e to the power t z prime is phi of e to the t sx. It's like the thing that maps under phi, right? Right? But this is phi of e to the ts times x, and by the property of x, this should be e to the power tsz. This is by definition of x. Maybe I'll just add here by definition. By definition of z. Okay, so I have verified that for every t, so this is true for every t, right? So e to the tz prime equals e to the tsx, tsz, right? So e to the tz prime equals e to the t times sz. This is for all t. And now again, by this differentiation trick, if you differentiate both sides, which you can, it's an exponential, you can always differentiate. You differentiate at equal to 0. On the left-hand side, you get this z prime, and on the right-hand side, you get this sc. Okay, so it's easy. What about preserving addition? That's a little bit more tricky, and this time, not surprisingly, we have to use this Lie product formula. So phi x plus y equals phi x plus y. It's part of linearity, so I shouldn't have separated it, but okay, so it's clear what I'm doing, all right? So how do we verify this? So again, let's try to write the definition of this phi x plus y. So what we know by its definition, e to the t times phi x plus y, it is capital phi of e to the t times x plus y. Okay, it was the exponent that was defined by under the image of phi for the one parameter subgroup, right? So now I would like to use this Lie products formula for tx and ty. So then this will be the limit of phi. Okay, maybe I should first write as phi of the limit of e to the tx over n, e to the ty over n to the power n as n goes to infinity. Oops, where's the limit? Oh, limit is inside. Okay. So now phi is continuous. So the limit and continue and phi commute, right? So I can write this as limit of phi as n goes to infinity of phi of e to the tx over n e to the ty over n to the power n. So now I can break this into phi of each part, right? So I can write it as a limit as n goes to infinity of phi of e to the tx over n, phi of e to the ty over n to the power n, because phi is a homomorphism, and finally phi of e to the tx over n. Well, x like this phi of this exponential is described by this little phi of x, right? So this is the limit as n goes to infinity of e to the little phi of tx over n and I can put the 1 over n outside because phi is a scalar invariant. I've just proved that. Okay. Then e to the phi of ty over n to the power n. So here I'm using the fact that phi preserves the scalars. Preserves the scaling, okay? And now what do I have on the right-hand side? Again, I can use the Lie product formula, this time for phi of tx and phi of ty. So by the Lie product formula, I end up with e to the power phi tx plus phi ty, which is e to the power t phi x plus phi y. All right. So I have showed that e to the power t of the phi of sums is e to the t of sum of the phi. All right. So now from e to the t times phi of sums equals e to the t times sum of phi's. And differentiation at t equal to 0, again, we obtain phi x plus y equals phi x plus yy. So again, the two exponentials are the same for all t, so when we differentiate, they have to. Everybody happy? Is it clear what we did? Maybe. All right, so just to scroll up a bit. So for showing that phi preserves addition, we started with the definition of phi of the sum. This is like the it's the guide that gives the one parameter subgroup of obtained by phi composed with e to the tx plus y. Now I use this Lie product formula for the thing inside, and then composition with phi is possible because phi is continuous, limit, and phi commute. And now we have this expression, which is really the Lie product formula for phi x plus phi y, or phi tx plus phi ty, whatever. And then by equality of the two exponentials, we see that phi x plus y, which is the exponent, equals the phi x plus yy, which is the other exponent. All right, so we verified this one. Which one is left? So we verified linearity. Did we verify conjugation invariance? Not yet. So one is left, right? Is this the page that I'm looking at? Okay. Maybe okay, let's verify. This shouldn't be, yeah, I think we can verify it now. Yeah, okay, we can verify it now. But before that, I think basically we have the uniqueness now. All right. So now we can verify uniqueness of phi from the third, from this condition. Okay. So uniqueness of phi. So let's prove uniqueness. The uniqueness. So for uniqueness, but basically we need to see what this phi is. But okay, so what is the role of phi? So we know that phi e to the tx equals e to the t phi y phi x, or rather maybe I should write it as e to the phi tx, and phi preserves scalar, so this e to the t phi x for all t in R and x in G, right? This is by the definition of phi x. But I applied the definition to tx, but I use the fact that the scalar can come out. I proved linearity of phi anyway for whatever phi is there, okay? Am I right? Well, I mean, I proved this linearity for this particular y. Maybe I should be a little bit more careful. Okay, okay, I guess, all right, so suppose that we have linearity. Maybe the argument applies still, but okay, I'm a little bit sort of doubtful if my argument was 100% correct, but okay, anyway, so suppose we know phi preserves the scalars, then from this, again, when you compute the dt at 0, well, basically then you have phi x, right? So then phi x, and then it's just d dt of phi e to the tx at t equal to 0, right? Yeah, okay, so I might add something in the notes later just to make sure that this argument is 100% valid, because I'm not sure if linearity is there. So let me see. Okay, but we can continue for the moment. Okay, so and now what is left is this. Well, there are two things left. First, that it preserves the conjugation, which is number 1 here, and number 2 is the Lie bracket. Okay, so we have basically addressed number 3 and linearity and so on. But now for number 1, again, let's start at what defines this g phi x g inverse. So let's start with phi. So now for maybe I should for number 1. For 1, so proof of 1. So which is this relation. Should I copy it maybe? Maybe I should copy number 1 here. Proof of, for better clarity, for further clarity. So this is phi of g x g inverse equals phi g little phi x phi g inverse. So this guy, it basically describes this one parameter subgroup. So this one parameter subgroup, which is like phi of e to the t gx g inverse. All right. So this is really e to the power. So this is just e to the t times phi of gx g inverse by definition of little phi. Okay. But on the other hand, well, I have e to the power some conjugation of some matrix, right? So then the conjugation can come down. I can write this as phi of g e to the tx g inverse by the properties of the exponential, the matrix exponential. All right. And now I can expand this as phi g phi e to the tx phi g inverse. And now all I need to do is I should differentiate both sides again at t equal to 0. On the left-hand side, I get the derivative of this e to the t times phi of conjugation. So I just get phi of the conjugation. And on the right-hand side, I get the derivative of this. But now this is just some constant matrix. I have to differentiate the thing inside. But that derivative is just e to the like little phi x by the definition of little phi x. Or rather by part 3 of this statement. So I get phi g little phi x phi g inverse, which is the right hand side. Okay? Are we on of time? Almost, but we have enough time to verify the last assertion that this phi is a Lie algebra homomorphism. So this is now the last thing. Proof of phi bracket equals bracket of phi's. So this time, we use this trick of differentiating the conjugation. So what is phi of the bracket? So this is, well, the bracket is just the derivative. So I mean, this is just xy minus yx. And remember that this xy minus yx was the derivative at 0 of something. So let's write that thing. So this is like d over dt of e to the tx y e to the minus tx at t equal to 0. Okay, that quantity inside will be like xy minus yx. Okay, now phi is a linear map. In particular, continuous. So phi commutes with differentiation. Okay, phi, in fact, because it's linear, like this derivative is a limit. It's limit of something minus something. So phi is linear, it commutes with everything. So I could just write it as maybe here, maybe I write. So by linearity phi. I can write this as d dt of this phi e to the tx y e to the minus tx at t equal to 0. Okay, but now by the conjugation preservation of phi, so this would be by part 1, by part 1 of this statement, I can write d over dt of capital phi e to the tx phi y capital phi e to the minus tx. And the phi of e to the tx's, I can relate them to little phi, right? So this is d dt of e to the little phi, like t times little phi x, phi y, e to the minus t little phi x. And I have to differentiate this guy at t equal to 0. Okay? But now again, I have to use the Leibniz rule. This time, the only thing that changes is that the matrices are phi x and phi y and so on. And when I use that Leibniz rule, it's just the same thing as here, right? Here, I knew that this commutator is just the derivative of this expression at 0. Now I have this other expression derivative at 0. And when I think about it, it's just that commutator phi x, phi y minus phi y, phi x, which is the Lie bracket of these two guys. Okay, so we started from this and we got to this, which is what we wanted to show. Okay. So next time we will look at further properties of this little phi, the Lie algebra, the corresponding Lie algebra homomorphism. And in particular, we see that we now have a so-called functor from the category of Lie groups to the category of Lie algebras. And another thing is we learn about the adjoint representation, which is an important group homomorphism from the Lie group G into the GL of the Lie algebra G. Okay, so I guess we can stop now. Are there any questions here or online? Are there any questions?